Test. Testing. 1, 2, 3. Can you hear me at the back? Testing. 1, 2, 3. Loud and clear. Can you hear me? Can you hear me? Can anybody hear me? Put your hands up if you hear me. Yeah? Okay. We'll kick off in about 2 or 3 minutes. All right? Grab some food, grab a drink, and then start to make your way towards the front, and we'll kick off the talks in a couple of minutes. Phoebe, can you jump on the live stream and see if the sound is any good? Can you jump on the live stream on Facebook and just see if it sounds good? Do you want to share your slides? It's all right, because I have like a little station down here. We're live on various platforms here, so. Yeah. You can just put it here. Yeah. Sound good? Cool. Showtime. Okay. Hello, everybody. Did I wake you up? Sorry. Okay, you can make your way to the front a little bit. Don't be shy. Is it loud and clear? You're the furthest. Anson, can you hear me okay at the back? Sound good? Cool. Okay. Hi. Hi. Who's nervous? Raise your hand. Okay. Right. Welcome to Piccolage Company. Welcome to the Pic Cafe, the newly renovated space. You're here in the South office. We've also got a North office over there for our Explore team. And also welcome to the Machine Learning Tech Talks. This is our third Machine Learning Tech Talk and our third Typhoon at the same time, every time. I don't know, I take it as a signal that we should continue to do these things. So, yeah. My name's Lawrence. I should introduce myself. I've probably been spamming you on various platforms over the past few weeks to kind of drum up some interest for the event. And it's really nice to see so many of you here. Oh yeah, you probably have figured this out by now, but we're live streaming to YouTube and Facebook and LinkedIn. So if you don't want to be in that, you can kind of go a little bit further back, and also keep the profanity to a minimum because, you know, we don't know who's watching. Hello, if you're out there. Yeah, we've got two speakers today, and their talks look very interesting, and I'm looking forward to learning from them. Basically, we hold these things to kind of build up a bit of a community here in Taipei and Taiwan, and you know, we're very excited and always looking for new speakers to join. I think Pound, are you here? I think, yeah, you've lined up for the next one, maybe in late October, November. If anybody else wants to talk at these events, just get in touch and we can, you know, discuss the topic. Yeah, so the talks today, we have Shannon, our very own machine learning engineer, who's going to talk a little bit about, I can cheat, I've got the title here, because it is a little bit beyond me. Interpreting latent representation in neural radiance fields for manipulating object semantics. I'll let her tell you what that means, okay? I work in people operations. I do my best to keep up, but you know. And then we've also got Gergely, who's here this evening, senior machine learning engineer from faculty, I believe. He'll be talking about less of a mouthful, but equally interesting. Learning, lambdas, XG boost models on lambdas, but again, you can explain it. Anyway, so let's give them a round of applause. And the format. Yeah, so there are some drinks, there's some food at the back there. Bathrooms and stuff are out there in the corridor. We've got masks and everything, you know, safety first. And we'll have a breakout halfway through the talks. I think Shannon will go on for about 15 minutes, and then we'll have a quick 10-minute breakout where you can talk amongst yourselves about what you've seen. I think, Dominic, yeah, you mentioned you might just do a quick show and tell of some magazines that yeah, cool. And then after that, Gergely is going to come on for another 15 minutes, and then we'll have a happy hour, and you can just hang around until 9 o'clock. I'll give anybody a office tour if they like, take a look at some of the space we've got here and on the north side. Otherwise, yeah, you're not here to listen to me. I will pass over to Shannon. Okay. And yes, Shannon, over to you. Yes.
Yeah, so hi everyone, I'm Shannon. Yeah. Today I'm going to share with you the work I did last year. So I know the title, yeah, it's actually my project title. I know it looks a bit lengthy and kind of intimidating, but don't worry, I've already highlighted some key points. So the first key point will be, I will introduce you the neural radiance field, and the second one will be manipulating object semantics. So this two is the key points for today. Let's take a look at the outline. Yes, as I mentioned, I started from the very basic concept of nerve. I'm not quite sure if anyone here have ever heard of it. I was still from the very basic concept. concept. And then we're going to the generated nerve is actually a derived property from original nerve. Yeah, so far the first section is more like the context of the entire work. So in the second section, we're going to explain and show you how really my work does is for controlling semantic changes in nerve, and then show you some experiment results. Okay, let's get started. Okay, when it comes to 3D representation in deep learning or in computer vision, there are lots of 3D representation. Like I just list some typical representation here, including point cloud, voxel, and mesh. I think you can directly see how this 3D representation different from each other, and there is one significant shortage shared by this 3D model is that when we need to increase the resolution, it will become a problem. For example, if we want to model 3D scene for using point cloud and want to get higher resolution, we'll need more points. And if we use voxels, we'll need more grid. So that will become an issue for memory usage. So people always want higher resolution. So people start thinking that if we can figure out another way to model 3D scene. So how about we just use the function to do that? Let's imagine there's a function called f that you give the function one specific spatial location. It will tell you what exactly the color or the density that spatial location is. We want to get this kind of function. So if you're kind of familiar with machine learning, you will know that machine learning network is exactly kind of function. So the concept of nerve is that we want to use some machine learning network to do this prediction. Let's see how it's applied in reality. Let's say here's a 3D space, and there's a tree in this space. We want to, I want to take a picture using this camera. So here we want to know what the color of this pixel is. There's gonna be a ray emitted from the camera lens going through the pixel and then going to the space. And along this ray, we can sample several points along this ray. Remember, we got a model, a network, or a function that can do a prediction for each point. So use this model, we can know the color and also the density for each point. I forgot to explain. The density here means you can imagine that kind of like the possibility that how possible these points contain an object. Let's say if a point is in the air, the density will be low. But if it's really belong to some specific object, the density will be high. So in this case, we use a model to predict color and also density. So you can see those points closer to the camera lens they're in the air, so they will have low density. But if it's the points belonging to tree leaves, it's actually something over there, so it will have high density and also the color will be green, right? And also there is some other points in brown. We can, maybe there is a point belong to the tree branches, then that will be something, so density will be high and so color will be brown. After getting all this information of the points along the rays, we can do some calculus with all the points here, and we will finally get the color of this pixel. So in this case, the color will be green. Yeah, this whole process can be applied to any viewing direction or any view direction. You can see here we want to model the underlying 3D scene, and we want to generate two images from different points of view. All we need is plenty of different rays and different sample points to do the image generation. Yeah. This is the basic concept of nerve. As you can see that right now we didn't define any parameter about resolution. We just show you how the rays work and how the simple points. So this model can be used for model very detailed scene. Right. Here's some results from our paper. You can see the scene are very complex and lots of detail in this. Yeah, and that's because this kind of amazing results. That's why when they're proposed in 2020, it's really caused a significant impact on 3D research area. And also there are lots of derivatives from this work. And we're going to introduce one of them. Yeah, this goes generative nerve. People, just as we mentioned before, that we can use one model to model one thing. So people are not satisfied with that, right? We want to use one model to, one more general model to model various objects, just using one model. So what we would do is that we add an additional input called Latin vector, so that if we put different Latin vector inside, it will represent different object with just one model. Yeah, that's basically the context of the work. So here comes the real problem we want to solve is that how can we control the Latin space to some semantic changes? And by the way, this is Mindy, our new app. It's already available to download. Back to the presentation. Let me redefine the problem. So what we really want to do is we want to search in the latent space and try to find some direction that can make meaningful changes in nerve. Like in this case, what do we mean meaningful changes? We want to make changes on specific parts. Let's say if it's a nerve for car category, we want to make changes only on roof or to make changes of wheels and hood, so some semantic region. So to achieve this goal, we can break the method into two steps. As I mentioned before, we want to do changes on specific parts. So we need to first identify where the part is, especially this is a 3D representation. Yeah, and after knowing where the part is, we can start searching for some meaningful direction that make changes only on that part. So what we do is that we extend it from original nerve. If you remember, the nerve can predict color and density of each point. We just add another branch called semantic branch. So right now the model can predict another semantic label for each point. With this kind of model, we can just when we generate image, we can also generate corresponding semantic segmentation at the same time. We did 3 kind of different data sets for experiments. You can see base, chair, and cars. And the second step is we want to go through the Latin space and find the proper Latin direction for semantic editing. Yeah, we use localization laws to optimize the direction for the direction searching. Let's see some results. So the left one, we will try to manipulate the roof. Yeah. And the right one, we want to manipulate the size of the wheel. You can see it's getting smaller. Let's see again. Yeah. And also we did experiment on human faces. The first row is the source image, and we can do some different changes on the mouth, so everybody close their mouth, and then nose, and also eyes. Yes, I remind you that we are doing something in 3D scope, so I show here the same woman, we do changes on her nose and show the result in different views. So you can see we do changes on those. And also the degree of changes is adjustable, so it will from the smallest nose to the biggest one. Yeah, that's all content for today. Let's have some brief summary. So first I introduce what NERF is. It's a new 3D representation which is very popular recently. And the second is that we do some semantic manipulation in our face generated model. Yeah, that's all for my sharing. Thanks for listening.
Do you want to stay there for some questions?
Okay, any question?
Yeah, we'll give them some time. I'll ask Shannon to stay here for a couple of minutes. And if anybody has any questions at this point, now would be a good time to ask. So yeah, I'll let you just mull on that for a second. If you've got any questions, I'll leave the awkward silence in the air. I'm sure Shannon is happy not to take any. I'll give it a few minutes, okay?
How long did that take?
So everybody, just chat with your neighbor for 1 minute, and then see questions. Come with your neighbors. Go.
Yeah, a little bit of time there. Okay, chat with your neighbor, come up with a question.
How long did I?
Exactly 15 minutes.
Oh, really? I think it's just super technical for them. No.
Right, this is still on. What I'll do, you put one here. If someone has a question, I'll take this around.
Okay.
If not,
So people ask questions. Where I want people ask.
not so far.
From image, the 3D shape, and using different models. Other patterns, and they also import these models into the community. And then use Unity to create, different things within that shape there.
Any questions brewing over here? I mean, okay, I've got a mic here. I'll bring it over. Well, just the people online, they can hear your question if I do that. We've got a couple of questions.
What?
We've got some questions.
Really? Oh, I hope it won't be too difficult.
Okay, I've been around, and I think some people have some questions now. Actually, John, it's a very good teaching technique. Okay, so I think there was, we've got one question over here, there's another question over here. Any questions over here? Yes, excellent. Okay, now we're talking. I'll bring the microphone over to you so that people online can hear the question. And I'll give you that. Oh, you can use that too. Oh, we don't have a portable, loud microphone. Would you like to go first? There you go.
Yeah, hi. Thanks for the talk. Awesome. It's like really difficult to break down a complex subject like that into a very short talk. So it's well done. Would you like to comment on the compute requirements for NERF currently?
Sorry?
Would you like to comment on the compute requirements for NERF?
There you go. I'll hold this one for you.
Yeah. So would you like to comment on the compute requirements for NERF?
Requirement.
Where you see the technology kind of heading from here? The compute requirements,
Oh,
because like,
Yeah, yeah, it will take lots of time for, like, we have several arrays, we need to do several calculations. It really takes time. So, for example, when I do experiments, for each experiment, maybe it will take a whole week. Or, yeah.
where do you see it going from here?
Hmm?
Where do you see the technology going from where we are today in the future? What do you think the changes are going to be in the?
You mean for what? Right now, it can already be used for modeling super complicated things. So some company I know apply this kind of technique into like furniture environment for furniture arrangement. Yeah. And also I think it can be also be using for AR or VR, some kind of virtual thing.
Thank you. Okay. I think we'll just go for one more question because of time and maybe saving you a little bit too. Here. We've got one here. We've got breakout afterwards if you want to kind of just chat with Shannon about it directly too. There you go. That's right. I'll hang around here.
Yeah, thanks for the talk. It's interesting. So, NERF is a new 3D representation, right? So, my question is there like some sort of how do I say this? Scenarios where you don't want to use NERF, or like the disadvantages of using NERF? Because I know there's an older version. So why do you want to go for this newer ones instead of the older ones?
Yeah, you mean why I don't choose some other representation?
Yeah. So NERF is a new one, and then the old one I think is called photogrammetry, if you know.
what?
Photogrammetry.
Photogrammetry?
Yeah, photogrammetry is basically like how do I say this? So photogrammetry is taking multiple images, for example, 3 or 4 images, and then they infer the depth from multiple angles. And then, for example, if you want to recreate an object, for example, a 3D object, you take, for example, I want to recreate this mic. Then I can take the angle from here, here, and here, and I will recreate this mic using those 3 images. That is one a very, very old technique. So and there is this new technique, which is invented, I guess, in 2020, I think. So why do we want to use that instead? Is there any disadvantages or
Yeah, the first disadvantage will be, just mentioned, the computation time will be very long and it will take lots of computation to do that. It's a main disadvantage. And why I choose this? First, because you can model more detailed things. And I guess, to be honest, because it's a silicon model, so we want to do experiments on it. So we want to explore what kind of potential it has. I think this is the main reason why I chose that.
Cool, thanks.
Okay. Right. All good. Thank you very much. We'll take a short kind of 5-10 minute break. Yes, thank you. And then we'll come back for Dave's talk in, I guess about just after 8 o'clock. So yeah, grab some more food, talk about anything you've seen, and see you a bit. Oh yeah, and then Dominic, do you want to come up and do a quick? Yeah.
Hi, everybody. My name is Dominic. So this is a great question. Who here has used Midjourney before? Who has not heard of Midjourney? I think everyone, it's pretty safe to say that everyone's heard of this. Who might have used it? And who is aware that there is a Midjourney magazine? Now you know, John, I know. So I just wanted to tell everybody, this is like there are some magazines that Midjourney has published that takes actual art from the community. I think the community votes on it, and they publish a magazine. There are, I think this is the fourth one so far. But you can also, it's really interesting, you can see like the versions from before V5, oh, thank you, John, to 5.1, 5 and 5.1, and see like the evolution of the model. So I brought these tonight. Everyone can check them out. Just a quick question. So this, including shipping, how much do you guess it would cost? Any guesses? Huh? $900 US. Okay, good guess. Three? Free? No, I don't. Unfortunately, it's not free. So, but Jaime is closer. This is $4 US. $4 US, including shipping and handling. So, just search for Midjourney magazine. Check it out. I mean, it's been interesting to kind of keep up with what's going on with this technology, and it's really cool seeing it printed out. It's much more tangible than on the screen. So I'll leave these. John, where's a good place to?
Just be here, so please come check it out. Okay.
Yeah, I'll leave them here. You guys can check them out, and yeah, enjoy.
Right. Yeah. Okay. Okay. Hello, everybody. Good evening, everybody. We'll just come back for part 2 of the machine learning tech talks. Okay, thank you. There's more space over in the middle here if anybody wants to take a seat. Okay, cool. All right. So we're on to part 2. We've got another 15 minutes from Gergely now. He's going to introduce his talk, and yeah, again, we'll have some more questions at the end. So if something springs up during the talk, just maybe keep a note of it. Maybe we can have a quick breakout again, and then we'll do the happy hour, wrap up, and go home in the rain. Okay, so I think I'll just hand straight over to you.
Yeah, thank you very much. Hi, everyone. I think I might have also overdone the technicality of the title and so on, so just bear with me a little bit, but hopefully there's going to be something interesting for all of you, some of you, any of you. So I bring some of my experiences learning working as a machine learning engineer, so that hence the stories from the trenches, a little bit, project that I worked on last year sometime. So a little bit of why am I here, what am I doing here? So I'm a machine learning engineer. There's an emphasis on the engineer side. On our company, the MLADs are doing the heavy lifting of making the models and so work, doing the actual things for the businesses that they need to do. I've been in various areas, various industries, so kind of just gathering all the experiences from different places there, and happy to talk about any of them because a lot of technology in all of them. So my company called Faculty, it's actually doing 3 different parts, and why we can collect that many experiences is because we are doing a lot of consulting for other companies. So this one is a story of a consulting project that we did for somebody else. So helping a lot of other companies do interesting machine learning that they couldn't do themselves, and that helps me to see stuff that otherwise wouldn't be able to do if I run a single company, just working on the same project for a very long time. And the project that we were working on was roughly along these lines, that there's a referral marketing company. Referral marketing means that maybe you are on a website, maybe you're on Shopee or somewhere else, you buy something, and then after you bought something, it pops up, oh, if you buy something more, then you're gonna get 20% off. Or if you get your friend to sign up, then they get 100 NT off, or so on. So this company was working with many other like merchants like that to do these kind of marketings for them, and they had 150 different merchants. Now, the way it works is maybe a client of that merchant, like you go on a website, maybe for Nike, try to buy something, and then this referral marketing company wanted to decide, using machine learning, whether they should show you something that is really valuable, like a referral code, or whether you are unlikely to use it, unlikely to share it with somebody else, and they should just show you like, oh, sign up for our newsletter, and like no point wasting money on somebody who wouldn't actually use it. So that's a high propensity to refer, high likelihood that you're going to bring in more customers, or low probability that you're going to bring in more customers. So they use this machine learning model of like whatever they know about that client to decide which one of the 2 way to go. So we are not really going to use this model itself, but we're going to deploy in this setup. And where the difficulty comes in is, a previous slide said there were 450 different merchants that these clients served. None of them wanted to share data with each other. Nike doesn't want to have their model trained on Adidas's data, or like vice versa. They don't want to let other people know that, like, okay, this is what makes a good referral person. So every different merchant had to have their own model. That means 450 model. And we want to have only a single server that serves all of these, because otherwise it's just going to be a nightmare to manage that. So here we are. We have a client that has a single server but want to serve 450 or even more if they sign up more clients to do clever machine learning for them. So now we get to engineering a little bit. So in a very broad, strokey way, the system looks something like you go on your phone or your website or on your laptop, you type in your merchant's address, and you go buy something, and then the middle box comes in place, which is our client's system of, should we do some marketing to this person? Will they share with their friends? Will they bring somebody on? Now, the new bit is on the right side. That's extra model of that separated machine learning infrastructure with the little brainy things as all the models, not 450, just 4 here for the interest in space. And this is what we want to bring to life in a way that middle box can work independently. And we set up the right interfaces between them that the right side is very effective. We have all the models going in there. It's very quick. It's very cheap because everything that the model uses is getting out of the profits of the company, but it does a good job. It's very fast, very cost effective. Now, this is where we want to get to, and I'm going to zoom into what different parts going to do. But we are starting a little bit from the beginning of the story of making some models, because that features into that how you can make this one very, very effective there. And what we want to make it effective is something light, something easy to use, something very portable. And we reach into different kind of models, not that much of what Picolage doing here, like image modeling, like deep neural network and so on. These are trees, these are decision trees inside there, and all kind of tabular data modeling, which is very clever and very useful in there, but it's also kind of like slightly different beast. So XGBooster that I have a shout out on the right side, that's basically if you have tabular data, probably just want to use that one. It's going to work as well as you can imagine in most situations. Like it wins a lot of like showdowns for tabular data. Scikit-learn, on the other hand, it's instead of using the models inside of there, they're using all the transformations and cleaning steps in the pipelines that they provide. And we collect them, attach them to each other in a way that we can have like a complete quote-unquote model that is the pipelines and the decision trees inside there. The decision trees deciding whether you are a valuable customer or a sign up for a newsletter customer. And this allows us to have a very lightweight API, like a server in the end, that the transformations happen in a model, so we can train on exactly that kind of data that would come in when the request comes in. That, oh, what are the user gender, what are the browser, what are all these values there. So we don't have to do any special transformations in the server. We can be very quick, get the data in, give it to the model, and get it back. Now, we're exporting that model together out, and while we were working on this project, we found, as we wanted to make it really fast to serve, we found the Onyx framework, which is exactly for that one, like taking any kind of model and making it servable very easily. It's very cross-platform. XGBoost and Scikit-learn and so on, they are not very or not easily. So XGBoost alone, you can export it in a way as just a text file with all the weights and everything. But if you're together with those transformations that I just mentioned, that's not going to work. Those are code. So Onyx, kudos to Microsoft, I think, who were making it, made a very, very good cross-platform model deployment tool, and we are taking that one. Now, it's also very useful because while we were doing testing at how quick something, how quick inference goes there, how quickly we can decide, here's the data and whether you're thumbs up or thumbs down, Onyx can make it faster than the original native versions of these models. So less than 1 millisecond, you can have a model inference. And it's also made vectorized, which we didn't use here, but otherwise it would be very, very helpful that you can just put in a bunch of data and it's still below 1 millisecond that it gets done because it's a vectorized inference setup. And it's also very quick to load from disk, which is going to be useful for us because we're going to be loading them from disk all the time. So 15 milliseconds, so that's very short compared to how much the data takes on the network. So compared to that one a little bit, the network data transfer takes more like tens and hundreds of milliseconds and so on. So it's very fast, it's very good, it's cross-platform, we can rely on it, so we're gonna use that one. And I chopped up here a bunch of icons, but I'm gonna explain which one of them is what. And the top level icons are all kind of different components that comprise the system here a little bit. And on the left side, what I said upstream is that server of our client who is gonna ask us, what should I do with this person who just bought something? So they are the upstream. Well, we have a little API gateway that just to distribute the load when we need to when a request comes in, and we are using lambdas. That's hence the little lambda there. So serverless serving. So that's to make it very cost effective. Those are very light, quick running processes. It works very well when what you're trying to do is very short-lived. So we're going to use lambdas. But we have to get the models into the lambdas. So, and we have a lot of them. What we decided here is not going the normal way of here we have our lambda packaged up with all the 450 models that whenever they change, we have to redeploy them again. Instead of that, we're going to do that other green box there, which is a network file system. So it becomes a lot more like your computer here. The lambda itself is just a bit of computation. It's running a function in your code, but with that live model store, the EFS system, it also has access to disk. And it's network storage, so we can write there. On the right side, very right side, there's a little bucket. So that would be the object storage, which is our model registry. That's where we put all the models that we train. We could use that one, but then it would be very slow. That is slow and unpredictably slow in a way. So what we are doing is from the bucket, we copy what we need onto the live storage, and we have a lambda that is unlike most other lambdas that people are running, have access to disk and just load things from there all the time. But we still have like 450 models, each of them like 1 megabyte, like 100 kilobytes to 1 megabyte. So that's still a lot. Like we might want to do larger lambdas to fit all of them, but that wouldn't be very cost effective. We might not use them all. So what we're gonna do is a bit of caching. So we're gonna add a bit of caching to this whole system, and that's gonna power like the secret sauce in a way of having that network storage, which is quick to read, quick compared to the object store, but also cached in memory, so it's even quicker. So we add a cache that does two things at the same time. So this TTL cache, TTL stands for time to live. So there's a lifetime. When we are loading the models in, the clock starts ticking. If that model has been around for a while, which we said that how long that would be, it's just gonna get out of memory and load it again. So if we replace models in the network file system after that time to live, we can get the new ones anyway. We don't have to redeploy anything. It's gonna happen automatically in an hour, for example, if we set that one. And there's the second aspect of this cache is not just have a max lifetime, but it has a max size. So we can control how many models we want to have in the memory. So if we have a small lambda, then maybe we don't want to have that many in the memory. If we have a larger lambda, maybe we want to have them all. And the least recently used cache is kind of like useful for this, because if somebody bought something from a website, it is more likely that somebody else is going to be buying from that website as well, because it's probably more traffic to the website wherever people buying stuff. So it kind of makes sense. One, the TTL side of it to be able to replace things, and the LRU is that to keep the most frequently used models in memory all the time, and then just a little bit of Python code to actually do that. And just showing that path access is just like going from your own computer, like going in a file system, find the right file and load it up. Now, when we were tuning things, we found a bunch of useful stuff. For example, even if lambdas are short-lived, we wanted to keep them around a little bit longer. So we use this kind of provisioned lambdas. So lambdas that are always there. They not for free all the time, but it's cheaper than having an actual whole virtual machine there. And then just tuning that how many of them you're going to keep there. And we found that the smallest lambda is 128 megabytes, can already hold like 100 models there. So if you can scale it up a little bit, then we can hold all of it. If not all the merchants are so frequently accessed, we can just keep the smallest one and so on. And with this setup, we get to get down our own services response time to less than 60 milliseconds all the time. Like most of it was 4 milliseconds plus network, something like that, and everything else was much higher. Now, the funny thing is that client was saying, oh, it has to be below 300. And then when they seen how quickly it can go, whenever it was 75, they were complaining it's slow. It's like, it's still 1/3 of what you were asking for. And we get, like for this particular client, we get up to about 10 requests per second. It doesn't sound much, but it is something that is comparable, that a single lambda with a couple of dollars a month, you can run this whole system. And there were a bunch of lessons that we learned from it. And if you're doing engineering and similar angles, you can also hopefully take away a bit. So the biggest one I want to mention is that everything is a trade-off. So a lambda's lifetime, how long it lives, how big is the size of it, because the size of the lambda determines that how quick compute or how much compute Amazon gives it to. So a smaller lambda is also a slower lambda. Larger lambda is also faster lambda, but they don't tell you what is the relationship. You just have to figure it out yourself. What is the concurrency? What is the expected rate? All because that caching works if you have long-lived lambda, and if you cache, it takes shorter time, so you need fewer lambdas. But if you and so it all plays off from each other, that how many you have, and like it's a whole multi-dimensional parameter space that you have to tune for the specific use. And you can get crazy things like when our request rate went down, we actually had to do more work because things weren't as warm somehow. So a lot of mind blown in this system, for my experience. And so we find it like building a good mental model of how these things work is very, very useful, and making things very, very simple to deploy, so you can experiment with a bunch of different arrangements. Very quickly. And as any engineer probably tell you, or any infrastructure engineer at least, that monitor everything. Because if you don't see what's going on, then you don't know what to change when you need to change things. And finally is making good interfaces, that how your lambda is set up, how your system is set up, and how they interact with other bits of the whole system, makes it much easier to do these kind of tuning within your own area rather than the whole system, and makes it safer, makes you sleep better at night there. And yeah, I think that's all from me now. And thank you for your attention.
Yeah, I mean, maybe again. worked quite well. A couple of minutes to chat with the group, and then maybe we'll have some questions afterwards, okay? So break out for a bit.
Fine. Do I look nervous?
Based in London.
Yeah, yeah.
Have you visited the office?
Oh, I worked there for like 2.5 years before coming back. Yeah. Yeah,
You were in Oxford for a while.
so that's coming and going. Taiwan and England coming and going. Yeah.
Be nice, be nice. Yeah, okay. All right, good. I think we've got a lineup of questions. Okay, very nice. I'm glad to see the confidence is coming back. Okay, just grab your attention. Maybe back there, looking at me. Cool. So you said you might be thinking about a question over there. Might be thinking. Very tentative. Anybody over here? Okay, if not, yes, one over there maybe. All right, let's go to you first.
Yeah. Hey, nice to meet you. You can call me Tico.
Hi, Tico.
From Fergal, the head camera company. And I have a question about. I'm just curious about. It's really amazing to serve hundreds of models at a time, and then like you say, monitor is everything. So, do we have any mechanism to make sure the AI model performance, like the precision and accuracy that the customers will use the model to get the right predictions. Like, once the model fails, then your customer might be angry about it. So do you have any mechanisms to make sure the model won't break?
Yeah, that is a very good shout, and that one is more on the machine learning monitoring side rather than operational side. If operation fails, you see it right away. If the prediction fails, you don't see any time soon. So that one is much more involved because on the receiver end, whoever receives the prediction, they have to keep track of things, of what were the predictions made and so on, what happened, what was the action, and then all get fed back into the training. So whenever it gets retrained, then it's going to be monitored there. So that's one of the things of delayed feedback. You don't know it now. And also, in this particular case, whether you or not you share something, it's not an instantaneous thing. So there's again a delayed feedback. One thing that they use to test all of these is that when we are doing a prediction to some percentage of the cases, you just return a random one. And so you keep track of this one was a random, this one was a non-random prediction, maybe like a 5% level there. And you can use that one, whether the random outcomes were different from the ones that it was based on your decision. And if it's different, is it better that you're doing something or not? Because it can be that you can even make it worse. So it can even mean that your prediction actually brings down the share rate, which would be very bad. But in the end, it turns out our share rate went up. And this one, you can only see it by having some amount of randomized data. So you can compare it to an alternative. And the other bit is you have to wait enough in the system that you can see the results. So there it was like 3 weeks to a month delay. So it's very difficult. It's very difficult. So good question.
Yeah. Okay. So actually, they do have the monitoring mechanisms, but it takes a lot of time to monitor.
Yeah. So yeah, here it's not like, you know, LLM doesn't give the right, like, are people happy about the answer? You see it right away, or a picture, you see it right away. People like it, people don't like it. Here with this one, when people do actions or have some kind of behavior change or further down the line, your feedback loop is much stronger. But that kind of machine learning performance monitoring is a whole hornet's nest. Yeah.
That's right. Thank you for your answer.
Sure thing.
Thank you. And then, yeah, go ahead.
Yeah, so my question was actually, I think, a little bit in the heart of the operations, which is you're using a file system, and that's how you're managing pulling so many, and then you catch them and pull them back.
Yeah.
So my question is actually surrounding that file system, because I'm very interested in, with the lambdas like spinning up, running, and pulling in files off this file system, how does the EFS piece specifically scale, right? Or like what happens when you have many lambdas at once trying to access the same model? It might be in cache, or it might even get overrun if you have too many requests at the same time. So I'm just curious about
that is a good question. So the network file systems, their scalability is more on the Amazon side, for example. So they have also metrics monitoring of, okay, if this network file system, this many like input-output operations you can do at a certain time. So that was also within the monitoring system. And we could see that when the lambda comes up and it caches a couple of models, it jumps. When the hour is up and it refreshes its models again, there's a little spike. But we were so far away. It was like a 0.01% of our limit of the I/O performance. So this kind of this load doesn't really affect that one, but in other cases, when you load bigger files or much more lambdas, that could come up, and then you need to monitor the operations side this time, not on the ML side, of how things are going. And the other bit is that since it's read operations, that one scales much better. If it would be writing, that would be a whole different kettle of fish.
Okay, and then can you go into a little bit more when you're pulling it into the EFS and you're doing, I think you mentioned it was like a batch loading, right?
Yeah.
Can you go a little bit more into that? And also, this would be on the operation side, knowing that the batch loaded incorrectly and what got updated, what didn't, monitoring that and making sure that that operation was actually successful.
Yeah. So when a training run is done, so we control the machine learning model training side. So training run is done, all the models are uploaded to the bucket, to the object store. So we can see whether all that succeeded, that's good. If that's all succeeded, we kick off another job, which is using also an Amazon service that would go and copy from one to the other. I forgot what the name was, but I think it might even be called batch. Which we used for this one. So that kicking off a job, does the copying, and you can also look at it, how many files get copied. We also set it up that whatever files you don't have on one side, then you delete from the other side, so we can refresh things that way as well. So keeping the logs for that. but you're, I think, in the right direction, that the network file system is both very useful, but it's also harder to monitor and control because you need an active machine to connect to. And if you do it securely, you cannot access it to anything else, just the Lambda and the AWS services. So if you needed to fix something there, that was a little bit more like manual work of spinning up a machine at the right place and connecting it to it. Fortunately, we didn't need to, because the hosted services can do this kind of transfer in a reliable way, and that we can test and run all the time, and we can look at the logs. That's what happened. That we expected. We trained 450 models. 450 models were uploaded, and that's all done.
Okay. Thank you.
Sure thing.
Okay, I did see some more questions, but it is 8:35 and we do have some breakout time now and a bit of a happy hour. There's a few more drinks over there. I won't come back on, but I do want to have one last round of applause for Shannon over at the back, and also for Gregor. So yeah, thank you very much for coming here and talking today. It's been illuminating, I'm sure. Yeah, we're going to host more of these. So yeah, get in touch. I think, yeah, Pound, you mentioned that you might come here later in the year and do a sharing. I think some more of our members are also interested in doing that. Otherwise, I think we're good. Just enjoy the evening. If anybody wants like an office tour, come find me and I'll take you around. Okay, thank you very much. Have a nice evening.
Thank you, Lawrence.
Oh, welcome.
Oh, I'm not gonna walk away with this one. Otherwise, you're gonna find me there.
I'll just listen.